Thank you for coming. It's for me a great pleasure to introduce to you Marco Morandotti and Jose Matias. Jose is a professor in Politecnico de Lisboa, one of the big universities in Lisbon and Portugal. And Marco is a professor in the Politecnico de Torino. And they will deliver a course on, elasticity, calculus of variation, and the modeling of deformations. As you know, this is a very close topic to those we are considering in our group, right? So we are more in the dynamical aspects, but statics and dynamics is connected through quasi-static, and many of the topics we address, like problems with constraints or Tarpike properties in long time, are very closely connected also to the theory of equilibria and nonlinear elasticity. So for us, it's really a great pleasure that you accepted our invitation to come, and I hope you will like it here in Bilbao and in Deusto during these few days. Thank you.
Thank you, Enrique, for the introduction. It's a great pleasure for me, and I guess I can speak for both of us, to be here. And thank you all for coming here today. So as Enrique announced, this is going to be a course, I would say a crash course on some mechanical theories. And it's a relatively new one. It's 25, 26 years old, and it's called the theory of structure deformations. So we'll see. Okay, I hope it's legible. Apparently, if I cannot erase it, it's the only thing that's going to remain on the board, so it's going to be that. So before getting to the definition of what a structure deformation is, I would like to remind you some basic concepts that are related to the mechanics of mechanics of deformable solids. So when you're given a solid, say omega, in a three-dimensional space, what you want to do is to study its deformations. So there's omega here, and then usually you have a map that describes how omega gets deformed. So maybe you can call it y, and this is y of omega. And what happens is that the map describes for each point x that you've got here, where it goes after the deformation. So this is y of x. And then in general, you can write y of x as x plus u of x, where u is the real deformation. So the identity, because you consider the space, and then you see the offset from the starting point. And what is relevant in mechanical theories actually is the deformation gradient. So the relevant object is f, which is equal to the gradient of u. And many mechanical theories are built on this object f, which say if we are in the three-dimensional setting is a square matrix, 3 by 3, because you map a point in the three-dimensional space into another point in the three-dimensional space, so u is from omega into R3. If you consider more general space dimensions, then this is a matrix, which is not squared, so it can be a general rectangular matrix. So for mechanical purposes, one maybe considers operations on this matrix in order for it to be squared. For instance, F transpose F, which is the so-called Cauchy-Riemann tensor, and builds the mechanics on this. So what's relevant now is to be able to describe the effects of a deformation, and what is usually done is by using an energy density. So one wants to define an energy for each deformation u and find a measure to see how big, large, in some sense, this deformation is. And the idea is that when you have, say, this matrix F, you want to associate it with an energy density on F. So I'm going to abandon the notation F pretty soon. It's typical from continuum mechanics. I'm more used to U and its gradient. So what you want to study is an energy, say E of U, which is given by the integral over your reference configuration omega of the energy density W of the gradient of U. So if you want to be precise, you should put here X and then the X. And you want to study this object. So what is important and what the main analytical contribution that comes from applied analysis and in particular for calculus of variations is to be able to characterize the equilibrium configuration of a body, possibly subject to external forces, by studying the minima of this energy. So you want to find the U such that you go to the minimum of the energy. And it's a basic step in the calculus of variations that necessarily minima of the energy satisfy the so-called Euler-Lagrange equation associated with this energy functional. And these are equations that involve derivatives of W and the gradient of U. So the easiest case is when W of its argument is, say, 1/2 the norm squared. So this would be 1/2 of the gradient square, which is the Dirichlet energy of the body. And what you obtain is the classical equation of elasticity, which means minimizers of the energy, if you don't have boundary conditions, are harmonic maps. Okay, so U is in the argmin of E, implies that the Laplacian of U is equal to 0. Now, the argmin needs to be searched in an appropriate function space, and at this stage, it's not relevant for me to specify which is the appropriate function space because we don't have boundary conditions and we don't have anything else. But the idea is that you assume that U is a minimum, and then you manipulate the energy function a little bit. You compute the so-called first variation, and you see that this equation is the one that must be satisfied. So when you have a mechanical theory that describes the deformations of a body through a PDE on the deformation, then you know that it can be seen as the Euler-Lagrange equation of an associated energy functional. But the minimization of functionals is what the theory of calculus of variation is mostly about, so that's a, say, more confident area for me to move in. And I want to be able to give an alternative definition of a deformation, which is a structure deformation, for which I want to define an energy density. So the idea now is to introduce the structure deformations. Let me see. Pretty much. Okay, so the theory of structure deformation comes in as an attempt to say measure the effects at the macroscopic scale of both smooth microscopic changes and non-smooth microscopic changes. So why this need? So what, and I should say that the main reference for the original paper, the foundational paper, is Del Piero, Owen, from the Archive for Rational Mechanics and Analysis in 1993. So the idea is that when you're deforming a body, many different things can happen. Especially at the microscopic scale, you can have microfractures. And the fact that you allow for microfractures releases elastic energy, for instance. You know that a body breaks up if it's more convenient from the energetical point of view for the body to crack open than to undergo very severe stretches. So of course, this mechanism happens at many length scales, because microscopic changes happen at the atomistic bond. So when you break atomic bonds between one atom and another one, whereas what you see when you're seeing a piece of iron being deformed is a macroscopic deformation. So their idea was to try and find a way to bridge these two different length scales and to find a geometric description that could do this. So they defined a structure deformation as a triple. That should be a Greek kappa, G, small g, and big G. And the Greek kappa is the crack set, say. So this is a set. So kappa is included in your body omega. G is a deformation, so goes from omega into, say, in general you can do Rn, Rd, or maybe let's do Rn, Rn. Okay? And then the big G goes from omega into the matrices Rn by n. So small g is the macroscopic deformation, and big G is the microscopic deformation gradient. So micro and macro are opposed to the capitalization of the small g, big G. Okay, you had two chances, and which they chose this one, and so the big G describes these smooth geometrical changes, smooth macroscopic changes, and they are described through the big G. Whereas what describes the non-smooth ones, maybe blue is a good color for non-smooth, is this object which is called M. And these are the non-smooth macroscopic changes. So this is also called the disarrangement. The disarrangement tensor. Meaning that whatever non-smooth behavior in your deformation is happening happens, and it's described by M. Okay, so if you look at the U that I wrote before, the nabla U would be U and nabla U here. So if you have a deformation where the big G is the gradient of the small g, then this M vanishes, and then you do not have these arrangements in your material, which means that you don't have any ruptures, any internal ruptures. So that's a perfectly good model for elasticity. Whereas if you allow for these things, then you can also have plasticity and other hardening phenomena, for instance, or fractures, and then there's a way to recover the typical quantities and the typical objects in plasticity or fracture theory by means of the big G and M and some of that derivative. So you can also recover, if you take also the curl of M, you can also recover the density of defects in a body. So you can say use this language to describe defective bodies, for instance, those that have dislocations or other topological defects that might happen there. So far it can be quite an abstract way of doing things, and I'm going to say one more thing, and then I give you some examples. So the main effort that Del Piero and Owen put into proving this theory, other than building it, was to prove that every structure deformation of this type can be approximated by a sequence of simple deformations. And simple deformations are those that I would call the classical ones. So if I'm given a deformation where the big G is the gradient of the small g, so say a classical one, how can I approximate this one? And so they claim that okay, so let me erase this one. They have this approximation theorem. that says that for any given structure deformation, there exists a sequence of, let me call it U, simple deformations, okay, just this crack set and the U, that converges to it. So Del Piero and Owen have a background of continuum mechanics, so the convergences are going to be in the L infinity norm, okay? And the idea, so the convergence theorem states that the set kappa is the lim as n goes to infinity of the set kappa n. Then they have that un converges to G in L infinity, and also that the gradient of un converges to the big G in L infinity. Okay, so this is in the uniform convergence, and it's a very strong convergence. I mentioned calculus of variations, and then I'll show you how to prove this theorem in basically 3 lines with some tools from say, modern analysis and the theory of functions of bounded variations. But before, I promised you an example of these, okay? So, by the way, if any notation or any symbol is not clear to you, just let me know. The lim of a sequence of set is usually defined as the union of the intersection of the tails. So you take kappa n, you do n from p to infinity, and then you take p from 1 to infinity. And this is your crack set kappa. Okay? So one example is what they call the broken ramp. And it is like this. You're given the domain is the interval 0, 1. So we do things easy in one space dimension. We take no crack set, no discontinuity set of the deformation at the end, and we want to consider a deformation which is to x, meaning a stretch. You take your interval and you want to stretch it by 2, and then I want to have a microscopic deformation gradient which is always equal to 1. So my problem here is how can I approximate a function which is to x by something which has gradient always equal to 1. Okay? And the idea is that they build this sequence un and un of x is x itself plus k divided by n if k divided by n is smaller than x is smaller than k plus 1 divided by n. Yes. So let's see how the sequence works. This is 1. And this is 2. So we want to approximate this deformation here, which is to x. And then at each n, I take n equals to 1. So how many k do I have? I have 0, so I never see this part, and I have x. So my first piece of my first element of the deformation is this one, is the identity. Okay, so u1 of x is equal to x. Now I look at what u2 is. I always have here the 2x. Now, when I have 2, I can break the interval. So k plus 1 can be 2, so k can be taken to be equal to 1. And what do? I have this one at 1/2, basically. So I proceed as the identity until 1/2. This was too much, sorry. So this is what I want to approximate. I proceed as the identity until 1/2 here, and then I jump by 1/2. And then I proceed as the identity again. So this is 1/2. This one is 1/2, and I've jumped by 1/2, so this is 1. Okay, and here I get to 3/2. Then if I go ahead and do the one this is u2 of x. So if I do u3, I basically take the interval 0, 1, I break it into 3 parts. I do identity in the first one, a jump by a third, identity in the second piece, a jump by a third again. And my 2x will be there. And I do this on and on. So what's happening here is that I always have something which has slope 1, which complies with this, okay? And in the limit, of course, my small g, so the un will converge to 2, because I keep adding jumps at a finer and finer scale, so I will converge to 2x. So it's actually not too difficult to prove that un converges to g in L infinity, and that the gradient of un is always equal to 1, which is the big G. So the point here is that in order to achieve this with this...
Sorry, yes, but there are jumps, right? So then you will have Dirac deltas on the gradient of u, right?
Yes, I'm getting there.
Okay.
So this is the absolutely continuous part of the gradient. So this is the classical gradient, which never sees the jump parts. So when you take the classical gradient, you always see 1. And then you can actually do this process at the cost of adding many, many jumps. So if one takes a step forward and sees what the distributional gradient is, and let's indicate it with the du. This is nabla u in the as a coefficient of the Lebesgue measure, and then there's this sum of deltas centered at this points k over n of amplitude 1 over n each time. So now the summation is not precise, but the idea is this one. So for each n you get, so this would be 1, this is the un, and you get the deltas there. So in order to achieve such a deformation, one needs to break things up and to introduce discontinuity, basically. And a nice way to do this, a very a way that has a very good functional framework, is to discuss this in the context of functions of bounded variations. So now I will abandon the description given by Del Piero and Owen, where you have all these nice uniform convergences. And I will move to a setting where you need to introduce, where you can model functions that have discontinuities. So this is done by introducing the space BV of omega, say with values in Rn. And this is the set of functions u that live in the space L1, such that the distributional gradient of u is a Radon measure. And the space BV is a subset of L1, and it's a nice and a good space, for instance, for studying fractures. There is a structure theorem for the distributional derivative that was proved by Ennio De Giorgi that says that du can be written as something which is absolutely continuous with respect to the gradient, to the Lebesgue measure, and it's indicated with the symbol nabla u as the gradient that one was always used to take. And this is what you see if on a set of full measure. Okay, so you have your patch omega of the Euclidean space, and then you measure this one there. And then there is a singular part of the measure, which is usually indicated by the S of u. Now, in turn, the S of u can be written into two pieces. A part that can be characterized as a jump part. So when you have a function from R to R, you can have discontinuities, for instance. And if you have a jump discontinuity, then the jump that you make enters in this part here. And then there is something which is much more complicated, which is the counterpart of the measure. So the counterpart of the measure is supported on a set which is of Cantor type, so which has an intermediate dimension between the full space dimension and codimension 1, whereas the jump part can also be written as it has a density with respect to the Hausdorff measure, and this usually is the jump of U, tensor the normal to the jump set, and this is the density of a measure which is Hausdorff of dimension n-1 restricted to the singular set of U. So if you imagine a function on the real line, wherever you have a finite jump that goes into this part. And how do you measure the jump in one space dimension? You do the right trace minus the left trace, basically, right? And that's the amplitude of your jump. So if you have the Heaviside function centered at the origin, the right trace at the origin is +1, the left trace at the origin is -1, and you have a delta, positive delta in front of it. And that enters here. And it is supported on that singleton, that's the origin where the Heaviside function jumps. Okay? So for the Heaviside function, the nabla U would be always equal to 0 because it's flat on the real line. And then you have a discontinuity here, which enters as a delta supported in the origin. A subspace of BV is the one where you just kill or you just assume that the counterpart doesn't exist, which still is the case of the example that I just gave, the Heaviside function. And so you call SBV, the special functions of bounded variations, with values in Rn, functions in BV, such that the counterpart is 0. Okay? And SBV is a good enough space for doing a lot of mechanics and setting up variational problems for mechanics. So now we are ready to give the same notion of structural deformations that Del Piero and Owen gave in the context of these function spaces. And this was due to Choksi and Fonseca. So let me erase this one. So this is still on the archives, 1997. And they say that small g big G, notice that there's no set anymore there, is a structural deformation in omega if it behaves like this. So if the first component is an SBV function and the second component is an L1 function Rn by n. So now the justification of this, if you're not familiar with these spaces, that I would like to invite you to consider is G is playing the role of a deformation gradient, and you need to do energies on those. So you need to integrate deformation gradients. So the minimum requirement that you want to have is something L1, basically. And then since the small g, say, has one order of regularity more, then you take it as BV. So SBV are L1 functions where the derivative has a special structure, and that's the right setting for making the objects talk to one another, and the small g talk to the big G. The gradient of the small g talk to the big G. And the kappa that was used before by Del Piero and Owen now can be identified with the singular set of G. Kappa was where discontinuity happened, and then the discontinuities are measured by the set S sub G that I introduced before, S sub U, which is where you concentrate the measure that jumps. Okay. Now, the approximation theorem is easily proved considering two ingredients. One is a paper by Alberti, I think in the Journal of Convex Analysis, 1991, which is a Lusin type property for gradients, or something like that. And he claims that for any, I have a consistency with symbols, so let me spy on my notes. For any f Now let me forget about the setting and the function spaces or the dimensions. But for any f in L1, there exists a function u in BV such that, and also a function h Borel measurable, such that the distributional gradient of u, so the full derivative that defines BV and SBV, is f times the Lebesgue measure plus h on hn minus 1. And moreover, the total variation of h in omega is controlled by a constant time year only data, which is the L1 norm of the f. So this is a very powerful theorem because it tells you that any L1 function can be seen as the gradient of an SBV function, essentially. And then the second ingredient B is an approximation theorem in L1 that says that for every u belonging to L1, you can find a sequence un, piecewise constant, so a sequence made up of piecewise constant measures, functions, such that un converges in L1 to u, and again you have a good control on the norm. So the L1 norm of un is controlled by a constant times the L1 norm of u. So now what do? I take f.
Sorry, can I ask you a question?
Yes.
So the gradient has to be rotational free, right?
Here.
So du is what?
Du is the distributional derivative.
Is the full gradient.
Yeah, this is the full gradient. And
so the rotational of the gradient is 0, right?
The kernel of u
the,
is 0 in the sense of distribution.
Yeah. So this must be 0, but in the sense of distributions.
Yeah, so what I...
So you're asking if this
imposes why are you considering all f's, right? So if I had to, if I was like trying to describe a function as a gradient, I will make sure that this vector field has, is curl-free.
In the classical sense, but then if this is not curl-free, then probably you can do that at the expenses of this h.
Okay, so this goes into
this
that
goes
side.
in the nasty part. Yes. So now what I can do is that okay? Okay, I'm given my structure deformation G, small g, big G, and then I take f to be the gradient of small g minus big G, which was also the object, the disarrangement that I had before. And then I apply part A of this recipe to f. So this tells me that there exists u such that the gradient of u is equal to f. So now the gradient of u with the nabla is the absolutely continuous part. So this is f, that is nabla small g minus big G. And this is by part A. And now by part B, there exists un, piecewise constant, such that un with the bar on top goes to u in L1. So now I define my un without the hat, without the bar, as my target, structure deformation G, and then I do minus the u that I found by Alberti plus the un bar. Okay? And this, I claim this to be my approximating sequence. And I should say that the convergence, no, I'll show you now. So what I can claim now is that un converges in L1 to G, because this part vanishes, because this is a piecewise constant approximation of this one. And then the absolutely continuous part of the gradient of un is equal to what I take here, nabla G minus nabla U. This one vanishes because it's piecewise constant. And then the nabla U is the nabla small g minus big G. So this is always G. And I can say that this converges weakly star in the sense of measures to the G. Okay, so it's just a sequence of constant objects, but that's that. So the approximation theorem, maybe I should write it here. Alla Fonseca reads that for any small g, big G, a structure deformation, there exists a sequence UN with the SBV regularity such that these two convergences hold. So what I want is that UN converges to U in L1, and nabla UN converges weakly star in the sense of measures to G in curly M. So this convergence must be tested against suitable test functions like continuous with zero boundary data. Okay, now the advantage of this formulation is that whenever I write an energy on an object like E of U, I can try and see what happens when I want to use that as to approximate a given structure deformation. So now the whole game here is to have an energy E of U of the type that I gave you before, like this. So now this is really not enough at this stage, because what I also want to have, since I'm introducing so many jumps and discontinuity, I also want an interfacial energy, something that penalizes in a way that if I'm breaking the material up too much. So I should add a term which is the integral over omega and the jump set of U, so which is concentrated on the jump set of U, of another energy density psi that depends on the jump and on the normal. Then this one keeps track of possible anisotropies in your material, so maybe the function psi has specific structure. Even a more general one can also depend on only the positive and negative traces across the jump, across the singular set. And then this one, since it's concentrated on this, I need to integrate it with respect to the Lebesgue measure of n minus 1. And there's x here, x here, x here. So José is going to give you some examples of work that we did on specific forms of this energy there. And then what I want to do, so the W can be general. Usually when you want to consider a mechanical energy, your W cannot be convex. You have notions of convexity that are suitable for higher space dimensions like quasi-convexity, polyconvexity. But if that's not the case, the first thing that you want to do is to relax. So you compute a quasi-convex envelope in a way, and then you want to see if that's good for finding minimizers. The idea is pretty much the same, but now the relaxation procedure that we're going to define involves passing from this energy defined over an SBV function. So this one is SBV because I need to be able to define all the pieces, to something which is defined on a structure deformation. So I want to be able to define I of a structure deformation, small g, big G, as here, as the relaxation of this energy, which means the most energetically economical way to reach this target structure deformation using functions that are here with this energy, meaning that I need to compute the inf of the lim inf as n goes to plus infinity. And then I want to compute this energy in my approximants UN with the conditions that UN are in SBV, because I need to be able to define an energy on them, and that the convergences a la Fonseca hold. So I want UN to converge in L1 to the small g, and the nabla of UN to go weakly star in the sense of measures to the big G. Now, to be precise, one should also include some boundedness of the total variation. or some other objects here, so some extra control that make the energy finite in a way along the sequences. I'm not going to give you the precise details of the growth conditions that you impose on the W because that would take up too much time. But so you need to complement here plus something according to the specific assumptions that you make on the little psi and on the W. Okay, you believe in that this is okay. When I have an energy defined like this, there's nothing I can do. So I can try and compute this inf of lim-inf, but then it's as general as it can be. So the idea is that one wants to give good conditions, and that will come into play as hypothesis on the energy densities, for which this energy I of small g and big G is representable as an integral. Okay, so the question is, does I admit an integral representation? Okay, so in other words, can I find so does the energy I is not like bad English, but so this is can I find big H and small h such that I can write the energy I of small g, big G, I suggest an integral, that's why, can be written as the integral over omega of the big H, so capital densities are always for the bulk part, of nabla G and small g and big G dx, plus the integral over omega intersection the jump set of G, of the H, the jump of G, the normal to the jump, dHn minus 1. So that is the question. Okay.
Sorry, Jose. The jump is always on a set smooth enough so that you have normals defined, or you have to understand that in some generalized sense?
No, it is part of the theory of BV and SBV functions that in the structure theorem you also prove that for the derivative, you also prove that the jump set is rectifiable. Mm-hmm. So it is a union, a countable union of regular surfaces. Mm-hmm. Mm-hmm. So for almost for Hn minus 1 almost every point, which means that if I'm doing a draw on the board, I can throw points away, so codimension two objects go away. But for the others, I do have a normal. So it can be something like a Shanghai type of thing, but then you just don't consider intersections where the normal is not defined. For any other thing, it is. So the answer to this question is yes. And the next question is, how can I compute the small h and the big H? And these are computed using the so-called blow-up method. Which is contained in some papers by Fonseca and Euler, and I think that there's one dating in 1993. I think that there are some works dating 1991, 1992. So the time frame is always about that, where they suggest this to study what happens at a specific point. You zoom in at that point, you explode what's happening there, and in order to find the big H, you impose some boundary condition in a minimization problem that are the easiest one that you can have for a, say, full dimensional deformation, which means an affine deformation. Whereas for this one, you do the same thing, but you approximate the easiest deformation that you can get, which is a jump between two values. So, yes.
It's the same blow-up method that Computational used for
I think so the idea of the blow-up method is that you zoom in at a point and see what happens there. I guess that...
So you have rescaling, like something like r squared?
Yes, you do that. So what you do here is actually that you prove that if you localize this integral functional, keeping the set into account, so in the formula that I just erased, you do I of small g, it's almost here again, of small g, big G, comma A, is the inf of the lim-inf of the energy defined as the integral on A. So as a set function, this one is the trace of a radon measure on the open sets of the open subsets of omega. And then you compute the cell formula in the blow-up limit by taking radon-Nikodym derivatives. And that comes up as a rescaling of something. So if Caffarelli did it in maybe two-space dimension, it had r squared. Here you have r to the n if the dimension is n. But the idea of that is that to compute a radon-Nikodym derivative of a measure with respect to another one, you take that measure on a small ball or cube and you divide by the other measure on the small ball, same small ball or cube. So if you want to take, for the bulk part, you need to take radon-Nikodym derivative with respect to the Lebesgue measure, and the Lebesgue measure of a ball scales like the radius to the dimension. And here you do the same thing with respect to Hausdorff n-1, which scales like dimension to the n-1. And then you see the interplay between those. Maybe I anticipated a little bit. Let me write down how you can characterize the small h, the big H and small h, and then we'll see. So now, this is defined on two different matrices, say A and B, which will be, their position will be taken up by the gradient of the small g and the big G. And this can be proved to be the inf of the integral over the unit cube, so Q is the unit cube, of the W computed at an nabla U, dx, plus integral over the cube intersection SU of the psi of the jumps of U, nu U, dHn-1, with the condition that U is an SBV function of the cube with values in Rn, and then I need to impose boundary conditions. And the boundary conditions depend on these two guys. So what I want is that U at the boundary of my cube is affine, so behaves like Ax, whereas the average over the cube of the gradient of U is B. So you see this now how these discontinuities are really needed for achieving this formula, because if you assume that U is at the boundary of the cube has an affine trace, say A is a constant matrix, then you want to have something which has one only gradient. But then you ask that the average of the gradient inside is a different one, right? So if you are in one space dimension, you might want to find something and the unit cube whose trace is like this, but then the average of the object inside is something like this. So you can't have say a more regular than SBV function that achieves this, right? So it means that you need to find a way to introduce some sort of discontinuities in here and move the pieces up and down like the sort of Venetian blinds in a way that you do things parallel to this, as I did with the identity before, but then overall you achieve a trace at the boundary, which is that one. And I want to stress the attention here on the fact that for computing the relaxed bulk energy density, so this is relaxed bulk energy density, both the original bulk energy density and the surface energy density come into play. Exactly because of this thing and the question that Enrique made before about the fact that you have to introduce many discontinuities, and all those deltas that appeared before needs to be diffuse actually in the bulk. So they diffuse in the bulk in the meaning that their Hausdorff n-1 dimension explodes to plus infinity, but in a controlled way, because all the estimates that I gave before on the total variation and on the norms keep them not too big. So the total variation doesn't explode too much. Actually, it doesn't explode at all. On the other side, you can compute this one, lambda eta, So lambda will be your prototypical jump, and eta is a unit vector for the orientation. This is the inf of the integral of a rotated cube by eta. So if cube was the unit cube, you pick an eta which is in the sphere, and then you rotate it. You rotate the cube in a way that it has two faces parallel to eta. And then we just minimize psi of this, with the condition that, again, u is in SBV of this rotated cube q eta. And then we want u at the boundary of the cube to be equal to a function that I'm going to define. I call it u lambda eta. And then I want the average over the cube of the gradient of u to be 0. So if I want to approximate an elementary jump, I just take something which is almost always flat on average, and I want it to be like this across an interface. Okay, so how do I construct that? I'm going to do a picture up here. This is your vector eta. This is the unit cube rotated by eta. And then the function u sub lambda eta is something which is, say, lambda up here. So I'm growing by this much, which is lambda, and then 0 down here. You should see it in 3D, it's just a crack. Okay? And so you do this at any discontinuity point of your target structure deformation. So you sit there, you zoom in. Since the surface is regular enough, you can start by saying, let me do it for easy things, flat surfaces. Then you do this. And you see something which takes two value. An easy one is 0, and any other one which is different from 0. And then you want this one to be matched at the boundary of the cube. So the trace of this needs to be this one, and the 0 below. And you've introduced the discontinuity here. And then you want to do it with something which is flat on average. Okay, so you can break it up, you can approximate it in a way that's optimal for this. Maybe sometimes you can really take this function here, which is the two flat parts here, as a test function, and then you take the inf over all these functions here. So my time is almost up. I'm happy that I could give you the positive answer to the question if an integral representation exists, and that I could show you the cell formula that allow you to compute, at least theoretically, this case. Computing these relaxation problems is pretty hard in general, and there are formulas available under specific conditions on the W and the original W, initial, say, a W and a psi. And Jose is going to give you some examples about this, and also some applications of this machinery, of this theory for relaxing a function, an energy functional, and define it onto structure deformations, applied to different problems. Okay, and on the technical side, let me just reiterate this once again. What you have to do for computing this h at values a, b, or lambda eta, you take a Radon-Nikodym derivative. So meaning that you see how much of this energy sees the Lebesgue measure and how much of this energy sees the Hausdorff measure. And those that come out are precisely these guys that enter at the end as the densities of the Lebesgue part and on the Hausdorff part. Okay. So, thank you very much for your attention.
Thank you, Jose. Do you have any question or comment before we switch? So this also is in close analogy. So probably this was earlier, but there was also all these developments in finite element theory on the Galerkin discontinuous methods, right?
Honestly, I don't know much about finite elements and Galerkin discontinuous, but there's I gave this a seminar on these things to someone at Politecnico di Torino, and the professor there came up to me and told me, oh, you know, the fact that you use that the small g, the gradient of the small g is not the big G, is actually something that we use in one of our approximation methods, because you cannot
Right.
enforce it at each step and you only want to recover it at the end.
Right.
So maybe it's discontinuous
Right.
Galerkin or
Yeah,
something.
this is discontinuous
I think it had
Galerkin,
a
yeah.
Japanese name or so, but I'm not completely
Sorry?
sure. I think the method had some Japanese sounding name, but I'm
Oh,
not sure
I
because
don't know.
I'm not an expert. Maybe that's a generalization of those.
Mm-hmm.
But what they had was an energy, say an energy functional in my language defined on objects that needn't be to be.
Well, of course, in numerics there is more rigidity because you put the grid.
Yes.
Then,
Yes.
You establish a priori what are the interfaces in which the jumps are
Yes.
allowed, right?
Yes.
Yeah.
Yeah, so here, if you're given a structure deformation, the interface is established already, but then the next step would be to minimize this. So if I'm given boundary conditions and an energy defined on structure deformation, I want to say what is the structure deformation that minimizes the energy under these constraints, and then this interface will also be a variable because the G itself will be a variable, and you want to find the minimizer.
And this link has not been done. I mean, there is no one has somehow
Minimizing this?
The finite element theory
Uh,
for these functionals and
Not that I know
linking it with discontinuous Galerkin.
of. Not that I know of. No. I don't think.
Yeah, actually, that would be a nice thing that like some estimates on this subformula, because we only know a very simple case that I'm going to speak about.
Yeah. Yeah, so these will be cases that are relevant for mechanics in a way, because there are, can I say a spoiler? No? I don't know. So, okay, so one of the results involves the W being equal to 0. So having no, say, elastic energy, no stored bulk energy density, and only working with interfacial energies. But because of this structure that you need both of them to get the new bulk, even though you start with a W equal to 0, you still need to minimize the psi to get the capital H, which means that in the relaxed functional, even though you started for something that was only interfacial, you end up with something which has both a bulk and a surface energy density. And for these, there are explicit formula for specific cases of these ones. And also, in another problem, we have a general theory and general results that we could also specify. We could only specify a little bit more in the case that W was equal to 0, because we could resort to those specific and explicit formula there. So, but at this stage, there's not much work done around, I guess, for this.
Are you giving some 1D example?
Uh,
Space dimension. All these make sense in one space dimension.
It also makes sense in one space dimensional, as the example that I gave before of the broken ramp was. Say that you want to achieve a stretch by 2x with allowing macrofractures in a way that you stay equal to the identity. Your deformation gradient is equal to the identity at the microscopic level. The theorems that we have are in general dimension, but if you
how will look this kind of augmented energy in 1D? I mean, with respect to the classical, say, half of the integral of 0 to 1 of ux squared.
So you would oh no, this is a sum. So this will be a sum over all the discontinuity points. So okay, if you're asking me how an energy of this looks like in one dimension is. The energy in one dimension would be something like, so you have a half of the gradient squared, and then you want to have something that counts of some density here that measures the jump of u at the point z. So this is a sum over all these. So if you have a function that has a finite number of discontinuities, this is a finite sum. If you have something more complicated, say with deltas centered at 1 over n, then you have a series in a way. And then if you kill this part, you only have that finite sum. Yeah. So then, thinking very, very further ahead, if you have something like this, it can be usually used for measuring, I don't know, maybe atomistic, like discrete models, and if you put a smallness parameter epsilon, you make the grid finer and finer, and you can have convergences to those, or ideally you could have something like that. Yeah, there are, I think, some papers by Owen and Del Piero, where they, or also Del Piero alone by himself, studied the energy of a one-dimensional structure deformation and trying to make considerations about what, like an easy way to relax the energy just by looking at the energy from some considerations, like where you want to put one discontinuity. If you constrain yourself to having one discontinuity, where should you put it, or how does the energy look like? Yeah. Okay.
Any other question or comment? Okay. Thank you.
Thank you very much.